Okay, so today we're going to wrap up section 3.2 over sequences and strings. So last time we started with the intuitive idea of a sequence as just an ordered list, which is in contrast to the idea of a set, which doesn't have any kind of ordering in it. So a sequence you can just write out as a list of things. So like the first, just the whole numbers, 1, 2, 3, 4, and so on, or the even numbers. And you can also have finite lists, so that don't continue forever, of course. So like the letters in the word discrete are a perfectly good sequence, or the digits in the decimal expansion of pi. Okay, but we also talked about the more concrete mathematical definition of what a sequence is. And it turns out that mathematicians and computer scientists, or at least the academic ones maybe, think of a sequence actually as a function whose domain is a subset of the integers. So this domain gives your sequence an inherent kind of ordering. So like the domain tells you the location in the sequence. So here's the first element, the second element, the third element, fourth element, so on. Okay. And then that location, usually instead of writing a functional notation like this, S of n, where n is the location, instead we usually just use a little subscript when we're talking about sequences. And this is what's called the index. You might have seen indexes in things like for loops and that kind of thing, or while loops. So finite sequences means the domain is finite, and an infinite sequence has an infinite domain. Okay, so we had those ideas last time, and actually this is the wrong copy of the notes. This is our copy of the notes from last time. Okay. So we talked about that, and then types of sequences. So these were things like increasing, decreasing, non-increasing, and non-decreasing sequences. Don't really want to get into detail on those again today. Essentially, the meaning of those terms is the normal English meaning. And this is where we wrapped up with the idea of a subsequence. And this is essentially just part of a sequence that you get by choosing terms out of another sequence. And for our example, we looked at the sequence of odd positive integers, so 1, 3, 5, 7, 9, 11, and 13. And then our subsequence was this 1, 3, 9, 27, 81, and so on. And these were all the powers of 3. And so you can get this sequence of powers of 3 from the sequence of odd integers by just picking the correct elements. So we would start with 1 and 3, and then we would skip a few up to 9. And then for the next one, you would have to skip all the way to 27 and pick it out. And then, to 81, and just continuing. That's where we left off last time. Were there any questions over that material before we talk about something new? No? Okay, so this is where we're going to start today with this definition. And what we're going to do is take a sequence, and I should point out that this is a finite sequence, which is important unless we're trying to do calculus. So we want to keep things finite, because we don't really want to get into the subject of calculus, because we're just trying to do things with computers in essence. That's why everything should be finite. And remember what this notation means. This tells you your index, I. And for this particular sequence, we're going to start at I equals m and then finish at I equals n. So if we were listing out the elements, we would write the first one am, and then go to the next one, am plus 2, am plus 3, and so on. And you'd get up to the last couple elements, an minus 1, and then you would stop with an, since that's your upper index there. Okay, so what we're going to do with this is something new. This first part of the definition is a sum. So the sigma, it's a Greek capital sigma, tells you to sum up everything in your sequence from I equals m to n. So this would be just am plus am plus 1 all the way up to an. So just adding a few more notes here. This upper number is your stopping point. And the lower number here is the starting point. Which matches up with our notation up here. So I should put the word sigma here. Sometimes you'll hear this referred to as sigma notation. Or if you don't really care about the word sigma, you might just say sum notation. And sigma, like I said, just refers to the Greek letter here, the capital sigma. Okay. And the pi over here, this capital pi, is standing in for a product, so P for product, or pi for product. So all we're going to do on this one is multiply all of these things together. So we would start at am, and then multiply by am plus 1, and then you just continue multiplying all the way up to an. And this is called product notation. So it's a shorthand way to write a long product is the idea. Just like this is a shorthand way to write possibly a very long sum. Any questions over the notation before we go on to the next page and work on an example? No questions? Sounds like someone might be logging in. Okay, so let's do an example. First, I need to give you a sequence. And let's look at the odd integers again. So an is equal to 2n minus 1 for n greater than or equal to 1. So, if you started plugging in numbers, 2 times 1 minus 1, you get 1. If you plug in 2, 2 times 2 minus 1 is 3, and so on. You'll get 1, 3, 5, 7, 9, etc. Just put a note here that these are the odd positive integers. And what I want to do is just add up some of them to get started. maybe add I equals 1 up to, let's say, 4 of AI. And this subscript here, this index, I should say, should match up with the subscript or index on your sequence. So here I used an N, but now I'm going to use an I to match up the two. But using a different letter doesn't actually change anything. We would still be looking at the same sequence of numbers. So this one tells us to start at 1 and stop at 4. So we would just look at the first 4 items in our sequence and add them up. So 1 plus 3 plus 5 plus 7. And what does that come out to? Anyone? $16, good. And you might remember, I think this was one of your problems on the homework, to find a formula for the sum of the first n positive integers. So you might remember that this is just 4 squared, since we're adding up 4 terms. So that does relate back to a homework problem that you've seen. Let's do a product. Maybe we'll choose a different starting point. Maybe I equals 2 to 4. Let's go a little further, maybe 5. So for this one, we would not start at the first one. We would start at the second number in our sequence. We'd start at 3. So 3 times 4, that's the third one. Oops. 3 times 5, excuse me, I said 4. And then the fourth one would be 7. And the fifth number in our sequence is 9. And that's where we would stop, since our upper index there was 5. And then just multiply those together. So what would you get? $945. Okay. Okay, and yeah, you can just use a calculator for things like these. You don't have to try to do it in your head if you don't want to. Any questions over that notation? That's about it for this particular idea, unless you have questions. No, okay. So if you ever end up taking a calculus course of some variety, then you would probably see this idea of a sum come up quite a bit. But we just need the basic concept for our class. And we're going to move on to something that I think is a little bit more common in computer science, strings. And we're going to talk a little bit about the mathematical concept of what a string should be. And you'll notice that this definition is maybe a little bit more general than what you're used to thinking about strings as when you're programming. A string over a finite set X is actually just a finite sequence. Of elements from X. So I think an important distinction between strings and a general sequence is that strings are strictly finite. You only have a finite number of things that are possible in your sequence, and it can only be a finite length. So when you're using a computer, strings are really the kinds of objects that you're going to be dealing with. not so much infinite sequences. So let's look at a little example. And for this particular one, our set X, where we're taking elements from, is just going to be 3 letters, A, B, and C. If you were programming, this would be a larger set, of course. You might have, any letter in the alphabet and lower and uppercase, and then numbers, the digits 0 through 9, and you might even have special symbols like periods and commas and that sort of thing, of course, that are allowed. But when we stick with just 3 elements, we can, write some little strings. And you'll notice that strings are usually written a little bit differently than sequences. Usually we don't use commas in between things in a string. Like this one, it's sort of a nonsense word, C-A-B-B-A-A-C. Not very many real English words that you can form from these 3 letters. But I do want to introduce a shorthand notation. You probably won't use this notation if you are programming something, but when you're doing math, sometimes it's convenient. And it works like this. So instead of writing 2 B's next to each other like this, what I can do is write B squared. And B squared would be shorthand for just B written next to B. And then I can write A squared instead of 2 A's. And so if I had, well, let's finish that word. If I had a different string, maybe this one, again, it's just a nonsense kind of thing, just letters. You can use larger exponents. So like here you have C, 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 C. So that you could write C to the 4th instead of that. Then you would have the single letter B. And then I have 1, 2, 3, 4, 5, 6 A's. So I could write A to the 6th and then finish up with a B squared. So one thing that I should point out is that you have to keep the same order as the original string. So remember, for sequences and strings, order is still important. Are there any questions over that idea? Either strings or the shorthand notation that we just learned? Yes, yeah, I just made up these strings. They're random letters, more or less. If you were programming something, you would probably see a word most of the time, something that actually made sense. Like one of the examples of a sequence on the first page was the sequence of letters in the word discrete. So this would be a string. But usually when we're thinking about strings, we don't use commas. It's pretty much the primary the primary way they're distinct, other than being finite. So you'll also run into an empty string, a string with no elements inside of it. So the notation that your textbook uses for the string with no elements is this. It's a lowercase Greek lambda. But when you're looking at a computer, the empty string would usually be written like this, something like quotation marks with nothing inside of it, or maybe single quotations. Okay. I think most computer languages use quotations uh, around strings, some variety of quotations. And since strings are finite, we can also talk about the length of a string. So if I just have a single letter, of course this would be a length 1 string. Or sometimes we'll use the notation that we use to count like elements in a set, or the magnitude of something. The vertical bars around A are shorthand for the length. Okay. And then if we had, 3 letters, like BAC, this would be length 3. Or using the vertical bars would be the same thing. Let me ask you guys, what's the length of this string? Someone want to try that one? 11, yeah, that's right. So remember, the shorthand notation just tells you that you would, for example, write 2 B's next to each other, and then 3 C's and 5 B's. So if we just add up the exponents, we can get the length. So we can think of A as having a 1 there. So 2 plus 1 plus 3 plus 5 would be a length 11 string. And then the same notation, the vertical bar notation, we can just write it out. For completeness. And one more question. What's the length of lambda, the empty string? 1. So remember, this is a length 1 string. This is what it looks like. And this is actually empty. Yeah, so if we were thinking of this as a character, a letter, then it would be length 1. But we're thinking of lambda as a stand-in for the empty string, so it is length 0. Good. So like I said, in programming, if you were actually working on a computer, you would probably use quotation marks with nothing inside instead of something like a lambda. But when we're doing math, we like to use things like letters and variables. Okay, so any questions over those ideas? Okay. So let's move on to the next concept. I suspect these are probably familiar to most of you who have taken a programming class. The next idea that we're going to talk about is the idea of concatenation. And this is just the idea of putting strings together to come up with a new string. The idea is we start with two strings, alpha and beta, then alpha followed by beta, so just tagging beta onto the end of alpha. For this particular class, we're going to write it using a kind of multiplicative notation, just write them next to each other. In a programming language, you might use a plus sign instead of writing it like this. I know in Python you would use a plus sign. I'm not sure how that would work in other languages. So just as a quick example, if alpha was the two letters P and Y, and beta was the string THON, then you could put those together, alpha beta, you would just have alpha followed by beta. This would be the word Python. Maybe I'll just make a note down here. If you were actually programming in Python, and I suspect other languages as well, though I'm not as familiar with other ones, so I can't say for sure. You would look at quotation marks around the letters P and Y, so that stands in for a string, and then quotation marks around THON, which would be another string, and the plus sign tells you to put them together into a single string. But remember, for our textbook, for our homework and for the lecture, we're going to stick to this notation like your textbook uses, so that we don't have to pick a particular language with a particular syntax. I guess I should see. Do you guys have any questions over that idea of concatenation, putting strings together? No? Okay, then there's one last thing we need to talk about called substrings. And a string beta is a substring of the string alpha if there are strings gamma and delta with alpha equals gamma beta delta. So this notation is maybe a little funny if you're not used to it. So what this is saying is that this string, whatever it is, beta, has to appear somewhere in alpha, somewhere in the middle of alpha, perhaps. So as an example, the string not is a substring. Oops. of this longer string to be or not to be. Because the string not appears here inside of the bigger string. So in this particular case, we could say, if we wanted to match up the notation, beta would be the word not, the string not. And then alpha would be this bigger string. And then the part before we get to beta, to be or, would be gamma. And I'm going to leave an extra space here because space could be a possible element of our set X, a possible character, let's say. And then the last part of the bigger string alpha would be what we call delta up here. And that would be a space followed by to be, period. Okay, so if you combine it all back together, alpha would be gamma, followed by beta, and then followed by delta. So just matching this back up to our notation here in the definition. Are there any ideas, any questions about that idea of a substring? Okay, so if there aren't any questions, that's going to be our stopping point for today.